We are on Unit 3. This is Notes 2. In this section, this is a huge section for us. This is a section on function analysis. Okay, we're going to look at graphs and different terms. You're going to be learning new terms. So this is a big section for us. I usually split this section up into 2 days. So I'm going to put this all in one video, but you can feel free to pause it, of course, whenever you need to and come back to it. Okay, I've started off by just sketching out a little curve just to give us something to look at. Something I want just to talk about some of these terms that we're going to be using, and I would like to, before we define things, I want to give them a little meaning to you. Okay, so first of all, whenever we see a curve like this, I want you to read this curve going from left to right. Okay, think about the leftmost x value. Okay, the leftmost x value. In this case, I labeled this leftmost x value u. Okay, sometimes this graph can go on and on and on. So the leftmost x, it's unbounded, right? So, but we would still read it from left to right. Okay, so we're going to start here at u, and we're going to go. X is going to increase, so we're going to go along this curve like this. Okay, so the first set of terms that I'd like to talk about is increasing and decreasing. Okay, increasing when you're starting on the left. Increasing is if you go up rather than down from here. So increasing, this curve is increasing at the beginning because the y values are increasing. Okay. Once we get to x equals a, then the y values begin to decrease. And then once we get to x equals b, the y values increase again. So the increasing and decreasing, they're talking about what y is doing as x is increasing. As x goes up, as x increases, what is y doing? Is y increasing or decreasing? So those are going to be intervals. We're going to have intervals where x is increasing and decreasing. Okay? The next term that I'd like to talk about is a relative maximum and a relative minimum. Okay? A relative maximum is a place where, like, this is a point where we have a relative maximum of this function, and it is so because there is an interval surrounding it. There is an interval surrounding it where this y value is the highest value. So if there is some interval around this point where this y value is the largest, then it is a relative maximum. It's not the maximum of this entire function, is it? Because we have some other values that are higher than it, but there's some interval where it's the highest. So this is a relative maximum. So f of a is a relative, and we're going to abbreviate that REL, relative maximum. This is another term for this is a local maximum. Okay, it's just another. AP uses those interchangeably because some textbooks call them relative maxes and some textbooks call them local. So AP will use both interchangeably. Okay. Same thing with a relative minimum, of course. If a y value is the lowest in some interval, so in some interval, if that y value is the lowest, then we call that a relative or a local minimum. Okay? So on this little graph that I sketched, f of a would be a relative max, f of c is a relative max, f of b is a relative min, f of d is also a relative min. Okay? A boundary cannot be a relative max or min. Okay? So you'll never include a boundary in a relative max or min. Okay? One thing that I should have included in the sketch is this situation. Let me come over here. Let me draw another little graph. Here I have a relative max. Here I have a relative min. And then I'm going to do something funky here. I'm going to do that like that. Oh, whatever. Okay? My point is this a relative max? So I ask you, is there some interval surrounding this point where this point is the highest point? Yeah, it is. So this is also a relative max. So it doesn't have to just be a hump. It could be a cusp, all right? Could be a cusp, and that's still called a relative max, all right? Okay, next up, so I talked about relative or local maxes and mins. What about absolute max or min? Absolute. So we also have this term that's an absolute maximum and an absolute minimum. An absolute max is the absolute maximum y value in a graph or of the function. Okay, so here I tried to make it clear what that absolute max and the absolute min would be. I tried to make it say, okay, I didn't label that one, but let me label that f of v. F of v here would be the absolute maximum of the function. Okay. And in this one, it looks like f of b is slightly lower than f of u. So in this case, f of b would be the absolute minimum value of the function. Okay, so we have increasing, we have decreasing, relative max, relative min, absolute max, absolute min. Next thing I would like to do is talk about concavity. So concavity is, let's get another color here. Concavity is, we can have things concave up and concave down. And I'm going to show you it, and then I'm going to explain how I'm going to show you the intervals here where it would be concave up or concave down. And then I'm going to show you how you can really figure it out. So from this point, from x equals u to what I think would be maybe around this point, maybe, this stretch right here is concave down. Okay, it's concave down. And then when we get to around that point, I could label that if I wanted to, but whatever that x value is, that from here to, and this curve got a little bit funky here, but maybe around there, I don't know, somewhere around there. This stretch of the curve is concave up, okay? And then we have another stretch here that from here to around there that would be concave down again, and then another stretch where it's concave up, all right? So that's visually what concavity looks like. I tell kids concave down looks like a frown. It has that little rhyme, right? Concave down looks like a frown. So here is our little frown, it's concave down. What confuses kids about that is sometimes we have a graph that's not completely a frown, it's maybe only half of a frown. For instance, we have a natural log graph that looks like that. This is concave down. Even though it's not a complete frown, it's still part of a frown. So even if it's part of a frown, we're concave down. Here's how to tell you guys. If you draw a tangent line, to the curve, is your tangent line above the curve or below the curve? That will tell you if you're concave down or concave up. If your tangent line is above the curve, then we are concave down. Okay? If your tangent line is below the curve, then you're concave up. Okay? What if your tangent line is half above and half below? Well, then we have a new term. This is called a point of inflection. I told you it was lots of terms this unit. So this is called a point of inflection or inflection point. Okay? So if your tangent line is half above and half below, that means that's a point where concavity is changing. So concavity changes at that point. All right? Okay, so I think that may be all of our terms. So that's just like a quick visual on what we're going to be doing this unit. Now let's take a look at actually how we figure things out. Before I leave this graph, I want to mention something. Back when we were talking about local or relative mins and maxes, tell me, this is something I would ask in class, and everybody would answer. Okay, tell me, what is f prime doing? What is f prime at a relative min or max? What's going on with f prime? Remember, f prime is the slope of the tangent line, right? What is f prime at a relative min or max? Well, if we draw the slope of the tangent, if we draw a tangent line at a relative max, what is its slope? What is this one's slope? What is this one's slope? The slopes there, the slopes here are 0. But remember I said that this would also be a relative min or max. What is f prime there? Well, f prime there does not exist, does it? So at a relative min or max, f prime is 0 or f prime is undefined. Okay? All right. That leads us to our last new terminology, okay? And it's also the first one that we're going to have an example on. Okay? A critical number. A critical number. Critical number. A critical number of a function is an x value at which f prime equals 0 or f prime is undefined. That's called a critical number. So it's an x value. It's an x value at which f prime is 0 or f prime is undefined. Okay? We use critical numbers because they are candidates. They might be a max or a min. Now, are they always a max or min? No, they're not. Because consider this graph. Consider that. Again, I got funkier than that. But anyway, you get it. What is the... I tried to make right here, there's a point here where there was a flat slope. Here, f prime is 0. But is it a max? No, because remember, a max or a min, it would have to be the highest or the lowest within some interval. And this y value is not the highest or the lowest within some interval. So this is neither a max nor a min. So just the fact that f prime is 0 or f prime is undefined does not mean that you have a relative min or max, okay? It just means that you have a critical number. And there will be times when you're asked to find the critical numbers. All right, so let's look at an example. Let's look at example 1 here. F of x is x squared over x squared minus 9. And the directions say find the critical numbers. Okay? So, to find critical numbers, we take the derivative and set it equal to 0 and see where it's undefined. So let's take the derivative. We're going to need to use the quotient rule here. quotient rule, start at the top, take the derivative, 2x. Multiply by the denominator, minus is part of the quotient rule. Now we're going to keep the numerator the same and multiply by the derivative of the denominator, and then divide the whole thing by the denominator squared. Okay, we are going to set this equal to 0, but before I solve this for x, I'm going to look at it because I need to find out if there's anything that makes this derivative undefined. To remember to find out where it's undefined, look in the denominator. What x values make the denominator 0? So f prime is undefined at x equals plus and minus 3, right? If you solve that little guy for x, you get plus or minus 3. So plus and minus 3 are critical numbers. Okay? Once we take care of that, now I'm going to multiply both sides by that denominator. When I multiply both sides by the denominator, it's going to go away. So I'm going to get rid of that because I have a 0 on this side, right? With what remains on top, I'm going to go ahead and distribute. So I'm going to, actually, no, I'm not going to distribute. I see I have a common 2x. So it's going to be easier not to distribute, but to take out that common 2x. So 2x I'm taking out. I'm left with x squared minus 9 from the first term, minus and an x squared from the second term, and that is equal to 0. The x squareds cancel out, and I have negative 18x is equal to 0, so x must be 0. So my critical numbers are 0, 3, and negative 3. Not too bad, I don't think. Okay, example 2. What about this one? G of x is equal to x cubed minus 6x squared plus 15. Okay, no denominator this time. Find the critical numbers. Okay, so we take the derivative. 3x squared minus 12x, set it equal to 0. Okay. In this case, again, I always check to look, see if there are any values of x that make the derivative undefined. And in this case, there are no values that make the derivative undefined. But always take a look at that. If you got a trig function, take a look at it. You know, some trig functions have asymptotes, so they will be undefined at places. So take a quick look at that. With what's left, I'm going to factor out of 3x. I'll have left x minus 4, and my critical numbers would be 0 and 4. Okay? So that's it. Those are critical numbers. All right. Now let's take a look at some examples involving increasing and decreasing. So increasing and decreasing. And remember that these will be intervals. Okay, back to our little initial graph that we looked at. I began talking about increasing and decreasing, and I said that right here, I said this was increasing, right? Okay, and I want to look at f prime here, and it's already drawn here. Here's the tangent line. This slope is positive, right? If the function is increasing, the slope will be positive, so f prime will be positive. If the function is decreasing, the slope will be negative. And it doesn't matter whether you're concave down or concave up. The slope will be negative if you're decreasing. Okay? So we can say if f prime is positive for all x in an interval a to b, then f is increasing on the interval. Okay, now pay attention here. If f prime is increasing on this open interval a to b, then f is said to be increasing on the closed interval a to b. Okay, so back here, let's take a look at from a to b here. The slope is negative between a and b. Right at a, the slope is 0. Right at b, the slope is 0. But in between, the slope is negative. Therefore, we say that f is decreasing here from the closed interval a to b. Okay? And you may ask why. Why is it closed interval? Why isn't it just the open interval? It's by definition. This is by definition. And most textbooks agree with this. Okay? Similarly, if f prime is negative for all x in an interval, in an open interval, then f is said to be decreasing on the closed interval a to b. And why don't we finish this up? If f prime is equal to 0 for all x in an interval, then f is said to be constant on that closed interval. Okay? All right, so in these next few examples, we are going to, let's call this, let's just call this, keep on going with our numbers. Example 3, I'm going to give you a function, negative 3x cubed plus 3x squared minus 4, and the directions would say find, and I don't want to write all this out, find the intervals where h is increasing, and then find the intervals where h is decreasing. Okay? On an AP test, they would ask you one or the other. Okay? They wouldn't be asking you for both. They would ask you for one or the other. I believe. I guess they could ask it like this, but it's a little bit, anyway. All right, let's go ahead and answer this question. So if I'm asked about increasing or decreasing, I know I need to find the derivative. Okay, so h prime is equal to, okay, negative 9x squared plus 6x minus 0. Okay, now I want to know where this is positive or negative, so I'm going to set it equal to 0 and get my zeros, and then I'll just do a little number line, a little sign chart. Okay, so once again, I would, if there was a denominator that made this undefined, I would go ahead and find it. I would put that on my sign chart as well, okay? But in this case, there is no denominator. So in essence, I'm finding my critical numbers. Let's factor out a negative 3 minus 2, like that. And then x is 0 and 2, right? I'm so sorry. This is a 3. Goodness. Goodness, goodness. That would be a 3x, not just an x, of course. So this would not just be a 2, this would be 2/3. All right. So now we're going to go and do a sign chart. Sign charts are pretty easy. We want to do a sign chart on h prime because we want to see where h prime is positive or negative, right? So h prime. Sign chart for h prime. I'm going to pick a value in here. So I think I'm going to pick like 10. Let's pick 10 because it's on this side. If I pick 10, I could either put it in here or I could put it in here. It's usually easier to put it into your factored form. Not always, but usually it's easier to put it in your factored form. So if I put 10 in for x, and I don't care what the number is, I only care what the sign is, right? This would be negative. This would be positive. Negative times positive is negative, so over here we have a negative piece. Now, because my factors are all single factors, because they're all odd factors, especially if they were even factors, we couldn't do this. But since the powers are both 1 for these factors, I know that my sign chart will alternate in sign. So all I have to do is find one piece. Hopefully I found it correctly because everything else is based on it. Okay? All right, now I can say that h is increasing on 0 to 2/3, inclusive by definition. And that is because h prime is positive on 0 to 2/3 open. Okay? H is decreasing on, okay, I want to go from negative infinity to 0, including 0. Okay, so I could say it like this. Okay? And 2/3 to infinity. Could write it like that, since h prime is negative. Goodness, one of those days. Not a good day for this long lesson, but that's okay. You guys will bear with me. Okay, h prime is negative on negative infinity to 0, parentheses on the 0, because it's not negative right at 0, right? And 2/3 to infinity. The other way to write this, you guys, if you wanted to, you could say h is decreasing on x is less than or equal to 0. You could, instead of saying that notation, you could use an inequality notation like this. So we can communicate our answers how we want to, as long as they are mathematically correct. Okay, so this means the same as that. So you get to pick. You can either use interval notation or inequality notation. I know for many, many years now, probably at least 3, probably 4, you have been taught to use this interval notation exclusively whenever you are writing an interval. And now we're saying, you know what? You get to decide. I want you to know both. Of course, you need to know both, but you can use whichever one you want. Okay? All right. Do I have another example? I do. Example 4. Y is equal to 3 minus x to the 1/3. And let's do the same direction. So let's find all the intervals where y is increasing and then all the intervals where y is decreasing. Okay? So we're going to begin by taking the derivative. Okay, we're going to have one chain rule, right? 1/3, 3 minus x to the negative 2/3 when we subtract 1 from the exponent, and then times negative 1 because that's the derivative of the interior. And then we're going to set that equal to 0. And now, again, I ask myself, does anything make this undefined? Do we have a denominator here? Well, we actually do have a denominator. It's a little bit hard to see because we have this written as a negative exponent, but that negative exponent means we're going to have a denominator, correct? So let's rewrite this where we have a denominator to look at. It's going to be negative 1 over, the 3 is in the bottom, and this 3 minus x to the 2/3 is in the bottom, right? Now it's easier to see that exponent. Or, I'm sorry, it's easier to see the denominator. So this is undefined when x is what? What x value makes the denominator 0? Well, 3 does. So x equals 3 is a critical number, and it needs to go on our sign chart number line. Okay? Now we finish solving this for x. If I multiply both sides by this denominator, which is legal now that we've taken care of what makes it undefined, I'm going to multiply both sides by that denominator and I get negative 1 equals 0. What x value makes that true? Well, no x value makes that true. So we don't get any x values from setting it equal to 0, but we did get an x value over here from this, what makes the derivative undefined. So here comes our number line. The only thing we're putting on it is a 3, and this is a number line for the derivative. Okay? So I always, if I can, I'm going to put 0 in, and I can here. So I'm going to put 0 in. It'll be on this side. And remember, you can put it in for what your first derivative is, or your first step in your derivative, or your simplified derivative. I'm going to put it in right here. So if I put in 0 for x, I'm going to have 3 to a power, and I know that that's positive, times a positive, times is negative. So this piece is going to be negative. Now let's come and put a number in over here. Let's put a number like 10 again, or 100 or something big. Okay, I'm going to put 10 in. So if I put 10 in, I have a negative to the 2/3 power. The cube root of a negative is negative, but then when I square it, because remember this 2 up here means we're squaring, we're going to get positive again. So this will be positive times negative, so this is still negative here. All right? So where are we increasing? Well, we're never increasing here. So y, I would say y is never increasing. Y is decreasing. Okay, how can we say this then? If we have to include the 3 in our decreasing interval, what would you say? You can say this several different ways. You can say on negative infinity to infinity, if you prefer interval notation, that will work. Okay? You could say y is decreasing on all x values. You could say it like that. There are different ways to convey this. All right? You could say negative infinity to infinity like that, an inequality notation if you wanted to. There are lots of ways to say it. Or you could just say y is always decreasing. That works too. Okay? So what this tells me is that whatever this curve looks like, let's see what this curve looks like. It must always be decreasing. So let's pull up, let's see what this looks like. But right at 3, that made it undefined right at 3, right? Remember, what does an undefined slope look like? Well, an undefined slope looks vertical, doesn't it? So we should have a vertical slope when x is 3. So if I put this in, 3 minus x to the 1/3, 1 divided by 3, and then I'm just going to go zoom 4. And there we go. It's always decreasing, isn't it? Always decreasing. So this makes sense. All right. Increasing and decreasing. Done. All right. Relative max and relative min. Okay. We touched on this. Let me pull back up. We touched on this when we were just looking at our little vocab, and my curve is really butchered up here, but I'm going to maybe come over here and look at this one, this relative max. We said that right at this x value, the slope of the tangent line is 0, right? And we said that our definition would be that the y value here is the largest in some interval surrounding it, right? In some interval surrounding this point, the y value is the highest. That makes it a relative max. Okay, so in that same interval surrounding it. My question is, what was the slope of the tangent, the derivative? What was the derivative on the left? And what was the derivative on the right? Well, the derivative on the left is positive. The derivative on the right is negative, isn't it? So here, f prime goes from positive to negative. Does that work for our sharp cusp? It sure does, because the derivative still went from positive to negative. That makes it a relative max. Okay? For a relative min, the derivative goes from negative to positive. That's going to be our definition, or that's going to be how we find the relative mins and relative maxes of a function. Now, the general term for that, or for both of them, is relative extrema. And that's mins, and maxes. Okay, extrema just means both, mins and maxes. All right, so relative extrema, let's say that f has a relative maximum, also known as, aka, local maximum, when f prime goes from positive to negative. Okay? This is called the first derivative test. Spoiler alert, we also have a second derivative test, but we'll get there. Okay. F has a relative minimum also known as local minimum when f prime goes from negative to positive. Okay, so f prime negative to f prime positive has to be a minimum. F prime positive to f prime negative must be a maximum. Okay? All right, first question on this, I think I'm on example 5. Okay. Let's see. Let's find all relative extrema on f of x is equal to x to the 4th minus 32x plus 4. Okay. By the way, let's just take a quick, before we just get too far into this, x to the 4th curves. We know a bit about x to the 4th polynomials, don't we? X to the 4th polynomials, they might look like this, right? They might look like this. They might look like this. Or they could be one big old like U looking thing. We know that x to the 4th polynomials have to look something like this. If it was a negative x to the 4th, these would be flipped. Okay? All right, let's find out which of these it is. All right? So, relative extrema, once again, rely on that first derivative. So that's where we're going to start, f prime. We're going to find the critical numbers. Okay? Critical numbers. So 4x cubed minus 32 plus 0, set it equal to 0. There's no denominator. If there was a denominator, That would go on our sign chart. We're going to be doing another sign chart here because we want to know signs. Anytime you want to know signs, do a sign chart. Okay? All right. I'm going to take out a 4. So then I have x cubed is equal to 8, so x must be 2. So we only have one critical number. One critical number. Come over here, sign chart. F prime sign chart, because we're looking for when F prime changes signs. Okay? So once again, I'm going to put in, if I can put in 0, I'm going to put in 0. It's easy to put in. I could put it here. I could put it there. Either one is pretty darn easy. If I put 0 right here, I get negative 32. So this is negative. Okay, and next up I can put something like 1,000 in. If I put 1,000 in, whether I put it here or here, we're going to get a positive. Okay, so F prime went from negative to positive at x equals 2, didn't it? So F prime went from negative, so we're going decreasing till we get to 2, and then we're going increasing afterwards. So it looks to me like we're looking at something like that shape. Okay, because there was no other flat spot, there was no other critical number, was there? All right, so okay, now it said to find the relative extrema. We found the x value where the extrema is, but did we find that did we find that minimum? No, we didn't find the minimum. We only found the x value where it occurs, right? To find the relative min or max, you need to find the y value. So let's go find the y value. We're finding the y value when x is 2. I get kids all the time say, Miss Murray, do you put that into f prime or into f? I'm like, well, what are you looking for? Are you looking for the y value of f prime, or are you looking for the y value of your function? You're looking for the y value of your function. So of course you would put it in for f. And by the way, if you put it in for f prime, you better get 0 because that's how you found that number, right? So yes, you put it in for your original function. All right, so 2 to the 4th minus 32 times 2 plus 4. So you put it back into there. And when you work that out, you're going to get a negative 44. So F has a relative, and you can abbreviate. For me, you can abbreviate. When you're writing your AP exam, you will not abbreviate though, okay? It's worth too much money to abbreviate. So just for me, you can abbreviate relative as REL, okay? And you can abbreviate minimum as MIN. So the relative minimum is negative 44. If you just can't stand not including 2, you can say at x equals 2. The justification, most of the time you're going to need to justify your answer, since f prime goes from negative, and you can abbreviate negative with a little negative sign like this, okay, to positive. There. Okay. All right. Probably have one more example here. I do. So next example, find the relative extrema again. Let's call this one G. And let's pull in a little trig function. And since we are pulling in a little trig function, I'm going to restrict that domain here. So we're not finding an infinite number of relative mins and maxes. We're just going to find a few. Okay? All right. Find the relative extrema again. So G prime, find the derivative. The derivative is going to be 1 plus, what's the derivative of 2 sine x? 2 cosine x. We're going to set that equal to 0. Now before we solve this, I want to take a look at this. Does anything make this derivative undefined? No, cosine is never undefined, so we're good here. So we just solved this for x. To solve this for x, if I subtract 1 on both sides, then divide by 2, I'll get x is a negative 1/2. And then I have a little trig equation to solve. What x values make cosine negative 1/2? Well, we need to go over to quadrant 2, and it needs to be a pi over 3. So 2 pi over 3. And then we need to go to quadrant 3, still a pi over 3. And we get 4 pi over 3. Those are the only two within 2 to 2 pi, right? So we're going to put those on our number line. Now on this number line, usually my number line just goes on and on if I'm doing a sign chart. For this sign chart, I can restrict it to 0 to 2 pi, right? And then I just put 2 pi over 3 and 4 pi over 3 inside. All right. And this is a number line for G prime, because we're trying to see where G prime goes from negative to positive, positive to negative, and so forth. Okay? All right. So is there anywhere easy in here? Maybe pi. Well, how about if we put pi in? If we put pi in, cosine of pi, that's a negative 1, isn't it? Cosine of pi is negative 1, so we'll have 1 minus 2, so this will be negative there. And we know enough about cosine to know that it's very cyclical, right? So it's going to definitely change signs around there. So if you find 1, you better find it well, and then you can just alternate those signs. Okay, so in this little section, the derivative is positive, so the function is increasing. And then in this section, the derivative is negative, so the function is decreasing. And then in this section, we're increasing again. Okay? So this gives us our max when x is 2 pi over 3, and our min when x is 4 pi over 3. But again, we did not find the max and min. We just found the x value that the max and min occurs. So we need to come over here and find the y values, right? So g at 2 pi over 3, we're putting 2 pi over 3 in for x. This will be 2 pi over 3 plus 2 times sine of 2 pi over 3. Here's where I would pause and I'd ask the class, what is sine of 2 pi over 3? Okay, got to know all those unit circle values. Well, it's positive because it's in quadrant 2, and since it's pi over 3, sine is a square root of 3 over 2. So this will be 2 pi over 3 plus square root of 3, like that. And that will be our relative max. Okay? And then g of 4 pi over 3 will be 4 pi over 3 plus 2 times, okay, sine of 4 pi over 3, it's in quadrant 3, so it's negative, and it's a pi over 3 where sine is a square root of 3 over 2. So this will be 4 pi over 3 minus square root of 3. So combining putting it as an intelligent sounding answer, I will say G has a relative max of 2 pi over 3 plus square root of 3 at x equals 2 pi over 3. Okay, justify your answer. So since G prime goes from positive to negative there, G has a relative min, or you can say local, of course, of 4 pi over 3 minus square root of 3 at x equals 4 pi over 3, since G prime goes from negative to positive there. Okay? So, not bad. These can get a little slightly long, but gosh, they're interesting, right? They're interesting. Okay. Anything else on this before we go on? I think not. So This is usually where I end my first day of these notes. So if you want to take a pause here, that will work. In fact, you know what? I think I might just pause this and make it into 2 videos. So let's end this one. I'm going to call it Function Analysis Day 1, and then we'll have Day 2 coming up.